Start recording. Okay, hello everybody. Welcome to day 4 of Handmade Hero. This is sort of day 2 of my sickness stream, so I apologize for my scatterbrainness, although let's be honest, I'm kind of scatterbrained normally. Last night was a bit of a defeat for us because we were just about to draw stuff to the screen and we didn't quite get to it. I elected to not push into the Q&A and take time away from that. I decided to go into the Q&A as we normally do, but tonight we are definitely going to start drawing stuff, but we are going to start with a very important correction, and I am very happy that that Chris Hecker tweeted at me because this is a good thing. I'm going to go ahead and launch our editor here and bring up our source code that we were working on, because after Chris tweeted at me, I realized what my confusion was yesterday, because I was a little confused, and I think you could tell in the stream I was a little hesitant. When I came in here to write Win32 update window, I said something like, should I use stretch to bits or shouldn't I use stretch to bits? I was kind of hemming and hawing. What I didn't actually fully explain at that time is the thing that I was actually thinking of using instead of stretch to bits, and what that was bitblit. And bitblit is the function that I normally use. I never actually use stretch to bits. I mean, I'm aware of it and I know what it does, but I never actually use it. I normally use bitblit. And so the thing that was causing the problem yesterday, and this is a bit of a bummer that I just didn't think of it, was that actually that is why there was the confusion about whether we needed to create a compatible DC. I remember S. Sylvan wrote in very helpfully to point out the fact that since stretch to bits takes a pointer to the bits, why do we even have to have Windows do this allocation stuff for us? And I was like, gosh, I don't know. And in my mind, I was thinking, well, I'm pretty sure you need to do it for performance reasons. But why was I thinking that? Because I don't normally call stretch to bits. But I just thought that that was true and blah, blah, blah. Well, the reason is actually because this is what I normally use. Bitblit is what I normally use. And if you notice, bitblit does not take a pointer to the bits. It has to go device context to device context. So what I was thinking in my head is I was thinking about the stuff you had to do to use bitblit, which involves creating a DC that you leave around that has the bitmap in it, and that you always do the bitblit from that DC to the screen, to the window DC that you're actually drawing to. That's what has to happen. So you have to do all this stuff because you can't pass a pointer to the bits. But if you call stretch DI bits, which I never do, you can actually just pass a bit pointer, which means you don't even need a DC or a bitmap. So the question is, why do I always use bitblit? Well, the reason, and this is why Chris's tweet jogged my memory, because he actually he's a pro at this stuff. I mean, he knows this stuff better than anyone probably in the world, because he wrote WinG, which was actually the first way that you could do this sort of stuff on Windows. It was under Win351, or Windows for Workgroups, whatever it was, Win3.1. You could actually do these blits to make games actually run on Windows way back before they could. And so he knew all about blitting on Windows, and he just knows that cold. And what he pointed out was stretch DI bits used to be the slow path. It was slower than bitblit because bitblit, since Windows could do the allocation of the memory and had the bitmap already selected, it was a faster path than going through stretch DI bits, which is why I've always anachronistically used bitblit. But since this is supposed to be for us to learn to write a renderer, and that performance difference may not even exist anymore. This was back when things weren't going through a 3D card under the hood and all these sorts of things. There's probably no reason for me to ever use bitblit. Stretchblit is probably going to be fine for us, because eventually what we'll do when we optimize things, we'll want to create an OpenGL context and actually write directly to a texture with overlap downloads and these sorts of things. So when we get to like the sort of, okay, we wrote everything ourselves and now we're going to start doing hardware things or whatever, we're going to want to do something different anyway. So really we can just use stretch DI bits, and I do not have to worry about the thing I was worried about, which S. Sylvan also was pointing out we shouldn't need to do. And he's right. I don't think we do need to do that. So with that correction in place, we can actually simplify things quite a bit. What that means is we don't actually need to store any of this stuff anymore. The HBitmap and the HDC that Windows was going to create for us, we don't actually need those anymore. Right? We don't need the bitmap handle. We don't need the device context. So all we actually need to do is have this bitmap info header filled out that has the width and the height correct, right? And then we can allocate the memory by ourselves. We can just allocate our own memory however we want to. And as long as it is the right size and works okay, Windows will go ahead and do the right thing. So that makes it a lot easier for us, and that's what we're going to do. So we're going to keep our bitmap memory here, but what we're going to do instead is we're going to go ahead and say note, thank you to Chris Hecker of Spy Party fame for clarifying the deal with stretch dibits and bitblit. No more DC for us. So this is awesome. So basically what we'll be able to do here is we'll basically just say, we need some memory. Windows, we need some memory for our bitmap. And the first question is, how much memory do we need? Well, we have asked for 32 bits per pixel. 8 bits red, 8 bits green, 8 bits blue, and I am going to leave a padding bit in there. Padding byte in there. So 8 bits of pad. And the reason that I'm going to do that is because, in general, on the x86 architecture, oftentimes there is a penalty for doing what's called unaligned accessing. So basically, if you are trying to operate on a value that's, say, 8 bits, 16 bits, 32 bits, 64 bits, this sort of thing, if you're operating on like 32-bit values, 32-bit values should be aligned on 32-bit boundaries, meaning they should be on like the 0th byte, the 4th byte, the 8th byte, and so on. They should not start on like the 2nd byte. They should always, if they're 4 bytes long, they should be at multiples of 4 in memory. And that's just the way the CPU is set up to deal with them. And so what I want to do is I want to make sure that whenever we touch a pixel, just for now, especially to simplify things and to make sure we're not incurring any penalties unnecessarily here, just to simplify things, I want to make sure that we're always touching a pixel on an exact 4-byte boundary there. So if we were to ask for the bits that we actually need for RGB, that would be 8 bits, 8 bits, 8 bits, or 24 bits. And 24 bits is 3 bytes, which is in no way aligned with 4. You basically have to go out 3 times 4, or 12, to get back to the right boundary, right? So that's not going to do it. So I'm asking for 8 extra bits that I need, and those extra bits are just going to be padding. They don't actually mean anything, and they won't actually be used, but we're just going to do that so that we know that our pixels are always aligned on 4-byte boundaries. So if that is the case, then I know I have a pixel size of 4 bytes. Right? That is how big that's going to be. So I need enough of these 4-byte pixels to have the width times the height worth of pixels, right? Because this is sort of elementary math. If you have a rectangle and you want the area of that rectangle, you multiply the width times the height, right? And so what we want to know is how many pixels do we have? Well, we have width times height pixels, right? But each pixel is 4. So if I was to make this a little more explicit, I might say bytes per pixel equals 4, and say that we have width times height times byte per pixel, right? So this is the size of our bitmap memory, right? And if we want to allocate it, we say the bitmap memory equals something that allocates bitmap memory size worth. Now, in Windows, how can we allocate something? Well, I like to use virtual alloc for a couple reasons. We could also use heap alloc. Either way, we are probably going to stick with virtual alloc mostly, so I might as well go and introduce it here. Basically what this does is it goes ahead and allocates a certain number of memory pages. And basically what happens is when you allocate memory directly from the system, it is generally allocated in pages, and pages are a certain size. In Windows, they are often 4096 bytes. Sometimes they are 64K. It depends whether they're large pages or small pages. That's sort of an operating system thing that we'll talk about a little bit later, potentially. But basically, there's 2 ways we could allocate memory. We could allocate it with heap alloc, like I mentioned. And heap alloc is basically asking the system to sort of sub-allocate out of the pages for you. So you can pass any size you want here, and you will get back a pointer to that. Whereas virtual alloc is a little more raw. Virtual alloc must give you back pages. So you can't, for example, ask for something that is less than 4096 bytes and expect it to give it back to you. What it actually will do is it will give you back the whole 4096 bytes, and the rest will just be wasted. I want to get you used to allocating memory from this, because we are going to be doing almost all of our own, we're going to be doing our memory allocation almost entirely ourselves in this project. So I just want to get started with this virtual alloc right away so you're used to calling it and it does not frighten you. So I'm going to call virtual alloc, and I'm going to look at the things here. We are going to virtual alloc our bitmap. And we are going to take a look, and it says it wants the starting address of the region. Now, this would be good if we actually wanted to place our, because remember, we have a virtual memory space. For those of you who watch the intro stream know, every process in Windows has a virtual memory space, its own addressing scheme for memory, and that gets moved out to physical memory depending on the how the operating system chooses to map it. But we are always looking at basically a nice big flat 64-bit address space that appears to all be our own, even though Windows behind the scenes is sort of swapping that in and out of physical memory, putting it to disk, doing whatever it needs to do to make it appear that way to us. But as far as we're concerned, we have a nice big flat address space. And as long as we don't use too much memory, we can kind of assume that we'll all be actually put in physical memory, so we won't have to incur any kind of weird performance penalty. So all we have to do here is say we don't actually care where the memory is, because we don't have any real restriction on where it is. We have to say the size, and this is the size of the region in bytes. Basically, if the address parameter is null, the value is rounded up to the, why is this scrolling? There we go. Rounded up to the next page boundary. So since we did pass in the LP address as null, it means that even if we pass something that is less than an even multiple of the page size of the system, it will just round it up for us, which is exactly what we want it to do. So that's totally fine. Then, we have the allocation type, and that is going to tell Windows what we actually want it to do to this memory range. And that the interesting thing about this is there's two actual things it can do. There's commit and reserve. And what's interesting about that is basically, since it is a virtual memory space, what that means is you start off with 64 bits of address space, but basically all of it is essentially vacant. It's not actually memory yet. And you basically have to say, okay, I'm announcing that these pages are actually now going to be used by me, so Windows can know, oh, okay, he's actually going to use some of this memory space. I have to start tracking it and working with it, putting it in physical memory, doing whatever I need to do with it. And it has a little page table basically that it keeps that says which pages for each process are actually being used. Now, what that means is when we go through virtual alloc, there's two ways we can ask for memory. We can ask it to actually start tracking the memory, and we're actually going to start using that memory, that's what commit actually is. But reserve is a separate thing we can do if we just want to make sure that memory is available for us and kind of tell you, okay, we're going to be using this memory, but you don't actually need to start tracking it yet because we don't actually need it yet. So why don't you actually just wait till I actually need it to actually start using it, if that makes any sense. So basically, we're going to use memcommit because we actually want the memory right now. So I'm going to go ahead and do memcommit, and then we can talk a little bit more about that later. Now, I don't think we actually need any of these other ones. We don't need to ask for large page support for any particular reason. We don't need address window extensions or anything like this. These are all things you do not have to worry about, and I don't think we will have to worry about either. And then protection basically says what we want our access privileges to be. Now, we do not need to execute code out of this memory, so we do not need the execute bit to be set. That is basically a bit that says whether or not the CPU can run code that is residing in that memory. This is basically for security purposes, I believe. Well, it could be for forking purposes too. I don't know. Don't get hung up on that. It doesn't really matter. Point being, we want full read and write access. We just don't need execute. So we're going to ask for read and write access to this memory, which means that our process can both look at the contents of that memory and store things to that memory, which we are going to be using both of. So we're going to ask virtualAlloc to give that back, and in theory, it will return to us, as you can see from the documentation here, it will return to us a void pointer. Remember, LP, long pointer to void, that is a void star. It is going to return us a void star, which is what we wanted, which is the memory that we needed. Now, if we should have to resize our div section and bitmap memory was already allocated, we want to just make sure that quickly before we do this, we go ahead and free that memory, because that is the only time that we actually want to do that. This memory is supposed to always be available to us, so we only want to free it if we think we're going to allocate it again right away. So basically what we're going to do here is we're going to use the opposite, which is virtual free. What you can do down here in the C also is they'll usually put things that are related. So if you want to know how to free something, you can usually go down here. Sometimes they'll tell you in here as well. Sometimes they won't. Here it is. Virtual free can free the memory. So what we're going to do here is we are going to go ahead and do mem release to actually get rid of the memory entirely. But I'm going to talk about mem decommit just briefly, just to let you know how that works, because we may use that in the future. Probably not here, but we will probably use it for other things on occasion. All right, so we are going to free the bitmap memory. We need to pass it the address to free. We need to pass it the size that it was, and that's the bitmap memory size that we allocated before. So it looks like we're going to have to store that, since I assume we cannot pass a null. Oh, no, we can't actually pass a null. That's good. So it'll just free it'll actually just free it remembers basically how we allocated, and it will free it. So that's perfect. So we don't even have to store the actual size. It'll do that for us. And then we just have to say that we want to release the memory back to the operating system, and it can reclaim those pages, use them for something else, give them to another process, do whatever it's going to do. It doesn't have to worry about keeping them back in physical memory on the hard drive. anymore. Now, when we do this virtual free, I said mem release so we can get rid of the pages. There's another thing we could have done. We could have done mem decommit. What is mem decommit? Now you notice we did commit over here, which basically said I want you to actually make these actual pages. Release makes them decommit, like stop being committed, but then it actually frees them as well. But instead, we could decommit them, but leave the pages reserved. So if for some reason we said, look, you don't have to pay attention to these anymore, but we're going to actually probably want them back later, so don't bother tracking them, but don't get rid of this memory range. That could be something that we might want to do. Probably not. I don't really know. The thing that we're more likely to do, I'll mention really quickly, because for some reason I'm spazzing out tonight. I'm just kind of in one of those zones where I'm just talking at you and talking at you and talking at you, and I see no reason to stop. Virtual protect is a way of basically taking something that we did with virtual alloc and changing the protection of that page. So one thing we could do, instead of freeing the memory, is we could choose to leak this memory in debug mode, meaning we will not free it, it'll just stay around, and instead of freeing it, we will actually virtual protect it. We will virtual protect it with no actual access. So we will go in there and we will change the memory protection memory protection constants of the page to be page no access, no execution, no writing, no reading. So that way we can't use the page anymore, even though it is still allocated. Now, why would we want to do that? The reason we want to do that is to make sure nobody has a stale pointer to the page. Because if someone kept a pointer to the page somewhere and they were going to try to write to it, that would be a use after free bug, which are very hard to track down sometimes. And so this is one way that you can catch those bugs. You can go ahead and protect the memory, make it so that you can't touch it, and then later when that buggy code tries to go and touch it, instead of perhaps succeeding touching it because it's still memory that's allocated by the operating system that got used for something else later, it will now fault right on the line of code that tried to do it. Great way to catch bugs like that. We will probably do something like that in the future to try to keep ourselves from making any mistakes like that. Right now, don't see much of a need to do that. I think we'll probably be okay. There's other tricks you can do with memory protect. We'll get into those later. But that's all I want to do right now. I'm going to step through this and make sure that we are doing the right thing. So I'm going to go ahead and type dev-env to bring up our project, and I will step into the Win32 resize dib section. So here we go. Let's make sure that the first time we try to resize our dib section, we expect our bitmap memory to be 0, which it is, which means we will not attempt to free it. That is exactly what we wanted. We will fill out that header. We know that's right. We checked that yesterday. 4 bytes per pixel, which is how many we expected. We will then ask for a certain amount of memory here, bitmap memory size. That is this, which looks about right, 1424 by 729 should be about that. And then when we multiply by the size of the pixel, which is 4, yep, we all good there, looks good. And now we will allocate our memory. And did we get it back? We did get it back, all is good. We are ready to rock. So now all we have to do is pass that memory to stretchdi bits to put it to the display, and that will solve our problem for us. Now what we're gonna do here is I think we're actually going to start. Now remember, we essentially do what's called a dirty rectangle update here. We passed Win32 update window, the region of our window that Windows asks us to repaint. But we could introduce some bugs here and make stuff harder for us to debug by actually using this dirty rectangle first time out. So instead of doing that, I'm going to have stretchdi bits just fill the whole window first. I'm going to have it draw to the whole window first just to make sure everything is working properly, and then we'll worry about doing a subregion that Windows wants us to do. So instead of doing it this way, I'm going to go ahead and look up that call right there. I figure like this will simplify our debugging a bit. It'll always start simple and then get more complicated. So basically we pass the device context we're painting to, we pass the destination, and so the destination, it's no longer going to be this at all. This is not what it's going to be. So the destination is going to be 0, 0, always, and then we are always going to do our full width and height, the full width and height of the bitmap instead of the repaint region. We're going to pass that, and then we will pass, I guess we should name this, so this is actually the bitmap width and the bitmap height, and then we will use the window width and the window height to make sure that we blit our whole bitmap to the whole window. Now, in order to do that, I need to actually know what size that is. So temporarily, I'm going to go ahead here and I am going to pass the actual window size. It might not actually be temporarily. We may just want to always know this. I think we do. So I am going to ask here for a window rect to be passed in that will tell us basically how big the window is, and then I will save the width and height of our backing buffer here. Again, these are global variables, not because these should actually be global variables. They're because we're just kind of working on getting the code working right now. These will not be global variables eventually. I do not this is not a good thing to leave these global variables, and we won't. So don't be thinking that you should put these things out there permanently. You should only put things as global variables when you're first getting things working and see where everything has to be. And then immediately after you kind of know exactly how things should go, you want to clean that up and make sure that only things that actually should be global are global. And that is what we will do a little bit later. So there we go. We have our global variables. And when we come through here and we resize things, we are going to go ahead and set the bitmap width equal to the width and the bitmap height equal to the height. And then we will go ahead and set using those from then on. So these will basically just be set there, and then we will just use those from then on. Okay, there we go. So that will be how we'll do that. We then just need to get the window width, and the window width, of course, is going to be, excuse me, the window rect. Let's see there. I passed a pointer to it because I didn't want to pass the whole rectangle on the stack. Didn't think that was necessary. The window rects, that will be the right minus the left to get us the width of it, and we will do the window height will be window rect bottom minus window rect top. There we go. And that should basically give us everything that we need to know. We have our bitmap memory pointer, but the one thing that I do want to know is what order, so stretch to bits, I'm giving it a pointer, but I don't know how it's going to read that pointer. How is it going to access that memory? Is it going to subtract, so how should I say this? So basically, it's going to look at that memory, and it's going to interpret that memory as a bunch of pixels, basically, right? And let's go ahead and do a drawing here so I can kind of get across to you. This is a bit of a visual point, and I think it might help to have a diagram. So I'm going to go ahead and draw one using GIMP with my magical drawing skills. I think we all agree that my drawing skills are kind of unparalleled. So let's see. Oh my God! Wow! Drawing with OBS is difficult. Oh my Lord. Okay, maybe this won't work. This is why I got to get a video capture card, ladies and gentlemen. That's almost impossible. That's almost impossible to do. All right, so that's a non-starter. There's no way we're going to draw that diagram. I will have to get a video capture card before I can actually draw diagrams. Oh, that's awful. Well, I'm glad we tried, because when it becomes more important, I'm going to need to be able to draw stuff, so we'll skip that for now. Basically, I'll do an ASCII diagram for you. All we're trying to do here is say, well, we've got a 2D thing, right, which is this bitmap, but we have a 1D representation of it, because memory is just a series of bytes. It's a giant series of bytes. So what we need to do is come up with a convention for storing something 2D inside something 3D. So basically, the X, a row of pixels is pretty easy to understand, because if I just give you a pointer to a byte, you can assume that you just start reading the bytes, and they are a row of pixels. But when you get to the end of the row, what happens, right? Do you just store the next row down on the image and then put that there? Do you store the next row up on the image? Do you back up? Do you do some pointer math? What's going to happen there? You need to know what happens at the end of the row where the next row's bits are, because basically you've got a series of 1D slices in memory you've got to reassemble into something 2D. Normally when I do things, I just tack them on. So it's just one row, then the next row, then the next row, then the next row, going usually top down. But we need to know what Windows is going to do. That thing is called a pitch or a stride, typically. The value is basically when you move a pointer, when you're going from row to row, typically something called, I think it's usually called a pitch. The value that you would add to a pointer to the first row to move it to the next row is called the pitch usually. And a stride is the number you would add to a pointer to the end of a row to move it to the next row. I believe that's typically how those two terms are used, but it doesn't matter. Point being, there is some notion of what you do, and we need to know which one of those stretch di bits uses. So let's take a look at the remarks and see. The origin of a bottom-up dib is the lower left corner. So you're talking about something where it starts down in the lower left corner. The origin of a top-down dib is the upper left corner. Now, I don't actually know which one those are, but I suspect that it has to do with whether we set the BI height parameter to negative or positive. So I'm going to go ahead and see if I'm right about that guess. Let's take a look. BI height. Let's see. The height of the bitmap in pixels, if BI height is positive, the bitmap is a bottom-up dib. Wow. The brain circuitry is still sort of working. Just barely, folks. Just barely. The bitmap is a bottom-up dib, and its origin is in the lower left corner. If BI height is negative, the bitmap is top-down dib, and its origin is the upper left corner. So you know what? I prefer top-down. I don't know if it's a performance penalty. We'll see. But we're going to go ahead and say that we're going to make this negative so that we can ask the rows to go sequentially from the top down, because I think that's a little clearer. That's usually the way people expect them to go. And so let's do that for now. That also aligns better with old school programming. Old school frame buffers started at the top and went down. And maybe you could argue that this isn't as good for thinking about new things in 3D where OpenGL wants them going the other way. And we'll take a look at all that stuff later. Don't worry too much about it now. But point being, I'm going to go ahead and do that now just to make things a little bit clearer for people out of the gate. Especially since Windows coordinate system is all top down, right? X is lower left to X starts on the left at 0, goes positive towards the right side of the screen, and Y is 0 at the top and gets bigger when it goes to the bottom. That's a top-down display, so it's kind of weird to flip them around. All right, so back to stretch DI bits. We now know we have a top-down window, so let's see what else it says here. If the parameters differ, they have different signs, create a mirror image. We don't want to do that. We're going to use the same signs, create top-down image. For dib is negative, so that's what we did. The function allows blah, blah, blah. But it doesn't really say what the stride is. It does not seem to say what the stride is here. Does the bitmap info say the stride? I don't think it does. So I guess we are just going to have to experiment, ladies and gentlemen, and see what the stride actually is. So we're going to pass that bitmap memory. We are going to go ahead and see what Windows does. Now, we have not put anything in it yet. So we're, this is something I should note, actually. One of the things that's problematic is basically when you do a compile inside Emacs or from the command line, sometimes MSVC doesn't give you the full path to the file name, and I would like it to give a full path to the file name. So basically when you hit CL, right, if I hit question mark, slash question mark, CL slash question mark, you can see that it gives me all the compiler options. And one of these options is basically to get full paths. And so I am going to go ahead and see if I can't get that to happen. I think I've got less installed on this machine. Do I? I do. So I'm going to go ahead and search for full. Let's see, use full path name, /FC. Okay, there we go. So FC is what we want in our build.bat. And let's see if I can go ahead and load that up. So let's get a -FC in there, see if that works. And it does. Look at that, full path name. So what's the nice thing about that is now I can just hit return on that in Emacs and it will jump right to the line. Or I can hit Alt-N, which is my go to next error, which makes it a little easier to find these bugs. So we changed the definition of Win32 update window. We certainly did. And so we have to go back and take a look here and call it the correct way. It needs to take the device context. It does. It needs to take window rect, which we have not passed it. So I'm going to go ahead and take this same code here, this that just got the client rectangle, and I'm going to pass that for now. We may want to clean that up in a little bit, but that should be sufficient. That is the rectangle that we wanted, the same one that we were using to resize our bitmap. So off we go. Let's run the code. We have not put anything in there, so basically what we're looking here is just to make sure we don't crash, because we don't know what stretch DI bits is going to do. We want to make sure we're passing it something at least semi-valid. We seem to be. So that is a good start. Now let's go ahead and actually draw those pixels. This is what I wanted to do tonight, and we are already there. I don't know if you can contain your excitement. You probably can't. Did Muratori for a syntax again. Said I wouldn't do it on the stream, and I did. We are going to go row by row through this bitmap, ladies and gentlemen. So we are going to start with a for loop that goes over the bitmap height, and we are going to look at each individual row, and for each individual row, we are going to go ahead and go over each pixel in that row, and for each one of those, did it again. Old habits, hard to break. Using the stream to try and break that habit. I know it's not useful anymore. What can I say? Old dog, new tricks. Sometimes it takes a while. All right, so we have our bitmap memory. It is a big old chunk of memory reserved by Windows for us, specifically for the purpose of writing pixels into it, but we have a problem. It is a void pointer, and a void pointer, as you know, is a pointer to something that C does not understand. So in order to start writing to it, we have to change it into a pointer it does understand. Now what I want to do is I want actual explicit control over the pointer and how it's going to move. So I want to tell C, first of all, basically that it is going to treat it as a pointer to just bytes in memory. So I'm going to cast this to a char star. Now I usually like to use unsigned char star, right? And these get sort of annoying to type. So one thing that we're going to do, and I'm going to start doing it now because why not, is I like to type def some convenient type defs here. Something that's a little easier to type and that means what I actually want it to mean. Because I really don't care about unsigned char. What I care is that this is an unsigned 8-bit integer. So I like to use uint8 for that. And basically, what you used to do in the old days is what I'm typing in right now, right? You used to do bitmap memory, there you go, you used to do that. But recently in C, and I forget exactly where these are defined. I think it's in standard type study. Is that a thing? Let's find out. Is that a thing? No, it is not. Is it in standard lib? I don't know where it is. Who knows where it is? Basically, there are new types that actually have the thing that you actually want, but I don't actually know where they are normally defined anymore. That is not correct, but I know you've got these, so I'm going to go ahead and search for where they are. They only just introduced them recently. Well, recently I'm old, so recently it's probably like 5 years, right? But I always had to do these myself back in the day. Standard int, that's what it is. But they've recently added these, and that's kind of cool. Basically, there are now types which are actually set up to be the correct size for your platform, because platforms used to differ in terms of what sizes things were. So if you said int unsigned, that could have been 16 bits, right? And that's no good if you actually needed the thing to be a precise size. So now that you can actually do that, I'd like to actually do that. These are the types that I used to use, and coincidentally C uses a type which is almost the same. But I like to define them to be my own way just because I am persnickety that way. You could just as well use uint8t. Anyway, that's something to think about. We're going to basically cast this to an unsigned 8-byte integer. And only reason I'm doing that is because I'm going to be doing pointer arithmetic. And as we know from the intro stream, anytime I add or subtract something for a pointer to move it around in memory, C will silently multiply that movement by the size of the thing being pointed to. So if I were to change this to a 16-bit, it would move by 2 every time. And I don't want to do that. I want to make sure I can do the arithmetic explicitly. Now that's just something I tend to do in pixel operations. The reason for that is because sometimes, as you'll see later on, they tend to have strides that aren't necessarily aligned on pixel boundaries for various reasons and stuff like that. It's just a better way to write these loops. You'll have to take my word on it for now. That's just kind of a better way to do it. But once we get in here, we can cast it to what we're actually looking at. And that is a 32-bit integer for going pixel by pixel. So basically what I will do is it's cast my row pointer here to that. And then at the end of each of these iterations, I will increment the row pointer by that pitch, which is the amount we're going to do to move it. And of course, the pitch is the difference between a row and the next row. That is basically just going to be the width times the size of the pixel, right? That is how big each individual row is. A row is width pixels wide, and each one of them is bytes per pixels long, so that's how big it is. So from row to row, that is the size, that is the pitch, and then each row I'm going to access here. Now again, this is maybe a strange way to write a loop. It's just a good way that I find to write pixel loops, because oftentimes this pitch value, you might say, looking at this, it's totally valid, and you're totally right to look at this and go, hey, wait a second. This pixel, I bet you're just going to do this in there, right? You're going to go ahead and increment this pixel every time right through the loop to write to the different pixels in the row. By the time you get to the end, it will already be right where this thing is going to be. Why are you doing that? It's inefficient. You're correct. The reason I'm doing it is because typically when we do these things, the pitch is actually not going to line up with this. And so it's usually easier to write them in this way for various reasons most of the time. But the other way we could do it is to just take pixel and add the stride here. 6 of one, half dozen of the other. Some may have performance concerns. Those are all things we're going to look at much later, so don't worry about it too much right now. That's just a good way to write those loops, typically before you're going to actually go in and start doing any kind of performance tuning. Now, I went ahead and added uint32 because we hadn't defined that yet. You know what? We could go banana cakes here, folks, and just finish off our typeset entirely and get all the different types that we might use. Well, not all of them, but most of them. Just get them in there. We will be moving these to a platform-independent header at some point because that's pretty good. So there we go. We've kind of defined our various sizes. Good to have on hand. All right, inside here, I'm going to use the dereference operator to write to this pixel. Basically, that says I am trying to access the memory pointed to by this pointer, which should be pointing to each individual pixel, and I need something to write in here. Now, what am I going to write in here? Well, each of these pixels is essentially packed in memory. This is the structure of the pixel. Pixel in memory, right? We basically have location 0, and that's going to be 8 bits. So we basically have, in hexadecimal, that is 2 of those things. This is the first one. This is the second one. This is the third one. This is the fourth one. Now the question is, we know we have to write R, G, and B. Which one do we write it to? And this is the pixel in memory. So this is basically the location 0 from the thing. This is 1 byte in, this is 2 bytes in, this is 3 bytes in from the pointer. So this is basically pixel plus 0, right? Pixel plus 1, pixel plus 2. Well, they're not really. It's only if that was. It's only if this was a uint8, right? Like I said to that. So this is pixel plus 0 bytes and plus 1 bytes and so on. From that pixel pointer, we are going in memories, right? So this is what that is. Now the question is, which one of those is red, which one of those is green, which one of those is blue? Now, if you were going in memory order, you would probably think, well, let's put the 8 bits of red there, let's put the 8 bits of green there, let's put the 8 bits of B there, and let's leave this as the padding byte that you said you were going to have. But what happens if we do that? Well, you know what? I'm just going to do that, and I'm going to let you see what happens. And in fact, you know what I could do? Just to, why confuse the matter? Let's just start doing it this way so I can show you fully explicitly. This will actually be that way, so we'll just actually do each individual one. We'll basically do the first one, so this will be pixel, and we'll increment it each time. We'll do this. We'll actually do it fully explicitly, right? So we write each byte in memory. Why not? Seems like a good idea, just to show basically what's happening. So let's say we were to write the red first. So, structured art is always a good idea to get things debugged. We want to see if we're writing to this thing properly. So we're going to just write to the red channel, and we'll leave the green and blue channels black for now so that we can isolate the red channel and make sure that we know how to write to it. All right, so we're going to write 0 into what we think is green, what we think is blue, and then what we think is the pad, we'll also leave 0, and then we'll just write the maximum value for an unsigned character, which is 255, into the red channel, or what we think is the red channel. And then we'll compile that and see how it goes. We will now go ahead and run this program. And first of all, we have to see, do we get anything on the screen at all? And you will see we do get something on the screen. But ladies and gentlemen, it is blue. Why is it blue? Why is it blue? Does anyone know why it's blue? Well, there are experts out there who know why it's blue. But I'm talking about people who took like the Intro to C course. I'm not talking about the grizzled veterans. You know why it's blue. Did you get it yet? It's tricky. But we did cover it in the Intro to C course. We did cover it. The reason is because this is a little endian architecture, ladies and gentlemen, which means, as I specified in the intro stream, when bytes are loaded out of memory to form a bigger value. So if I wanted to load 4 bytes and produce a uint32 out of them, the processor will actually put the first byte in the lowest part of those 32 bits. The second byte will go in the next part, and then the next part, and the highest will be the fourth byte over. So basically what happens is if these are the pixels in memory, if you were to load them into a uint32, you would load them R first into the low. I'm going to use the hexadecimal notation we learned. Here is our 32-bit value in a register. 32 bits now, it's one big value, right? The first 2, R and R, go down here. The next 2, GG, go in here. The next 2, BB, go in here. The next 2, XX, go right there. And look at that. It is backwards now, BGR. Well, the people who wrote Windows didn't like that very much. They were on a little endian architecture, and when they loaded a 32-bit value and thought of it as a pixel, they wanted it to look like it was in the right order when they were looking at it in the register of the CPU. So what they did is they defined the memory order to be backwards. So it would look like that, which means that it is swapped in the memory of the machine. So all Windows bitmaps actually have the blue byte first, the green byte next, the red byte after that, and then the pad at the end. That is basically how that works. And, well, there's really no other explanation for it than that. So what that means is if we actually want our red to show up as red, we need to move it to the third byte, and then we run it, and now we've got a red bitmap, ladies and gentlemen. Isn't that beautiful? And I argue that it is, in fact, beautiful, a very beautiful thing. Now, what we might want to do is start to make this a little bit prettier as we go. Let's see if we can do something a little bit cooler. How about we go ahead and assign just the x coordinate, casted down, so truncated basically, chopped off, if you will. Just take the lower bits of that value, and we'll go ahead and assign green into the Y channel, and then I don't know what we'll assign to blue. I guess we'll just leave blue black. Or sorry, I'm messed up now. This is actually blue, not red. So this is the red channel. That will be empty. So this way we can at least get a little amusing gradient going on. There you go. As you can see, much more attractive than what we were drawing before, if still not a game, at least something kind of fun, and it looks like it is all working correctly. And now you can see what I did there, pretty straightforward. I just said whatever our X position is, I'm going to take the low bits of that, and I'm going to shove it directly into the blue channel. I'm going to take the low bits of the Y, the row that we're on, shove that in, and so you basically get exactly that look. You get 256 pixels of increasing blue, and then it drops back to 0. 256 more of increasing blue, drops back down to 0, because that is just the 8 bits of the Y value going up and up and up. I hope that is pretty clear to people what's going on there. Won't belabor that point, but we can go over it in the Q&A if it is somehow mysterious to you. Now, ladies and gentlemen, we have done something that is rather remarkable, if you will. We have gotten ourselves back to 1980. That is what we have done. I could not be happier. But what just happened right before your very eyes is we have turned this modern, awesome, beastly computer running a hugely complicated and difficult to wield operating system into something where we just basically have a bitmap that we can draw to and get back to the joy of coding. Because there is no stopping us now. We can draw anything we want to that. But there is something we could still do. We have 20 minutes left in the stream, and 20 minutes is just enough to start to do some damage on something else we might want to do. So I say we go ahead and do it. I am feeling good tonight, ladies and gentlemen, even though I am sick. That is usually means, since pride cometh before the fall, that something terrible will happen to me in the next 20 minutes, but what can you do? I can't stop that. If it was going to happen, it was going to happen anyway. Might as well enjoy the last 20 minutes that you get if you're about to get hit by a bus or whatever it is that's going to happen to you. I say we move the rendering code for our bitmap up here into a separate function that basically says, what's this function going to be called? I don't know what it's going to be called. Maybe we will call it render weird gradient, because honestly, that is what it is doing. And the render weird gradient call will go ahead and take some kind of an integer. That will be the X offset and the Y offset. And all I'm going to do there is when we stuff our values in, we will add those offsets so that we can animate our gradient around the screen. Make sense? I think it makes sense. Seems like a good idea to me. And like I said, we got 20 minutes left, so how wrong can we really go? Now, if we want to reproduce the behavior of our own program, we can certainly just do that by calling render weird gradient right there, and we can pass 0, 0 to verify that we did not mess anything up. Now, of course, it needs to know how big those are, but we saved those, so that's fine, because the width and the height are actually global variables currently, so we can go ahead and use those right there. Let's go ahead and call int width the bitmap width. Then we will call int height the bitmap height, and then we are good to go. Oh, bytes per pixel. That is actually a constant. We will hoist that out for now. All of these things are things we're going to have to wrap up. I have a plan for this, by the way. I am not going willy-nilly. I do have a plan for how I want to do this, but we will talk about it in the Q&A if I don't forget, but I probably will forget. So maybe someone remind me, hey, Casey, you said you were going to do something, and you didn't do it. Let's verify that we reproduced our program when we abstracted that function out, and we did. We pulled it out all right. Good. Give ourselves a pat on the back. Now let's make sure that we can use our offset. I'm going to go ahead and offset it halfway on just the x-axis. X-axis. Talking, ladies and gentlemen, it is difficult. You've done it all your life, but it is harder than you think when you are programming live on Twitch. Okay, there we go. It is offset properly, just like we want it to be. So now we have every reason to believe that this function will work. But we need to do something if we want to actually make that animate, which is what I want to do. We need to go down here and not wait for Windows. We do not want to wait around while Windows stuffs in our message queue, because if you remember, I told you about get message A, and one of the problems with get message A is that it will block. So once we run out of messages, we will block right there. Windows will shut us down, and it will wait for another message to come to our queue. It'll go do other things, whatever the other things need to be, switch to another process, use that CPU time effectively. We don't want to do that. We want to use that CPU time all for ourselves. So really what we want to do here is we want to change this to a message loop that processes messages when there are messages, but if there aren't messages, we keep running, right? That's what I want to do. So we're going to go ahead and do that. Why not? We're going to go ahead and switch our message loop by the seat of our pants, ladies and gentlemen, to a peak message loop instead of a get message loop. Here is our peak message loop. And basically what a peak message loop does is the exact same thing as get message, but when there is no message, it will allow us to just keep on running instead of blocking. So we are going to go ahead and call that. You can see that it takes substantively the same things. It takes the address of a message, it takes the window handle and the filters, just like we filled out before. Don't need any of those. And then it has one additional flag that we need to know what to do. Basically, it's just something that says whether it should pull things out of the queue or just look at them in the queue and tell you what they were. Well, we actually want to process our queue, so we're going to pull them right on out of there, and that is PM remove. Messages are removed from the queue after processing by peak message. Go ahead and copy that out of there. Here we go. There we go. Not bad. Peak message. Now that's going to return a bool, and we need to know what that bool is. I assume the bool is whether or not there was a message, but let's go ahead and verify that. It's been a long time since I've actually written one of these loops. I always have the same loop I've been using for years, to be honest with you. Cut and paste reuse, that's the way you do it. Okay, so peak message, if no message is available, return non-zero. If the message is available, if no message is available, return 0. So all we need to do is say, if we got a peak message, then we are going to have to process it. Now, one of the things that we need to probably do is we don't want to repaint all the time, because if we had lots of messages in our queue, we want to process them all. So really probably what we want to do is we want to say while peak message returns true, translate and dispatch all the messages just to flush out our queue, because we're kind of obligated to process that queue. We can't not process that queue or our app will start being badly behaved. Maybe we want to gate limit that sometime just in case there's a flood of messages, but I don't know. Really, there's nothing you can do. You got to process your queue. That's pretty much just something you got to do. So we're probably just going to have to be stuck doing that. So let's do it. So this will flush out our queue. As long as there are messages in the queue, it will process them. But now we will no longer get our quit message. Oh, but that's okay. We don't have to worry about that because we are now using the running thing. But we should probably double check our message to make sure that we're not getting a quit message from Windows for some other reason. So I'm going to go ahead and double check that MSG structure. Let's see here, dot message. So dot message, I'm going to say that if dot message is equal to WM quit, I am going to make sure that running equals false, so that we just quit anytime we get that WM quit message, just to make sure that we're handling this case that we used to handle down here. Okay, so basically that will still do the exact same thing as before. We should have absolutely no difference now. Oops, we need the deleted the definition of the thing that holds the message. That's no good. Now, as we go, in theory, everything is now exactly the same as it was before, but we are now able to repaint our bitmap as often as we want. So what we could do is we could say x offset equals 0, and down here we can go ahead and say render weird gradient right in our loop. So after we are done processing our message queue, we are starting to get behind the Twitch window there, ladies and gentlemen. So I'm going to go ahead and switch back to this window here, so we are not obscured by the little picture of me talking, because who doesn't want to see me talking? I am sure that is everyone's favorite thing to do, is to watch my head. All right, here we go. We are going to call render weird gradient with the x offset and the y offset, and we are just not even going to bother initializing it in here. Not at all. Not going to do that because we don't actually care. We'll probably want to do in here, I'll put a to do, probably want to clear this to black. Probably clear this to black. But we don't need to do that right now or worry about that right now, because we'll be thinking about those sorts of things later. And what we will do is every time through the loop, we will take x offset and we will add 1 to it. Just go ahead and increment that using the shorthand for +1. Let's see what happens now. Oops, that doesn't look good. What's going on here? Well, that was not what we wanted at all. What happened? Why did my render weird? Oh, duh. Well, there's one thing we... Oh man, I was a little too excited there. I forgot something obvious. We need to still blit it to the screen. We need to actually update the window, right? Because we were only updating the window inside WM Paint, right? This thing that actually does the stretch bits, I never called it. So of course we're not going to see the results. Sure, we rendered to our bitmap, but our bitmap's not on the screen. We need to actually blit it to the screen. So let's go ahead and have that blit to the screen. Now we're going to need device context, we're going to need that window rectangle, and we are going to need the dimensions of the blit, which will basically just be 0, 0, and our window rect, our window width and height. So I'll go ahead and program those in there. Sorry for the little hiccup there, ladies and gentlemen. I don't think that was a big one. That was just a well, I got a little excited and was hoping I could do a little less work than what I actually had to do. But, you know, no harm, no foul. So window rect, at this point, This is something, now I'm just calling this out. I'm not doing it right now because we're just kind of messing with things at this moment. But you've seen me write this code a couple times with the, in fact, I'm just going to actually cut and paste it from here. You've seen me writing this code a couple of times. So right about now, if this were actual code that I wasn't just kind of funging with and was going to rewrite in a second anyway as we start to clean things up, which is what we'll do tomorrow, I would be pulling this out into a function and keeping this stuff. I would actually have a function basically that does this because we have done it enough times now that it's clear it's something we want to do, and I don't want to be cutting and pasting it all over the code. So I would definitely be doing that right about now. We're not going to, because I know that we're going to kind of funge. We're going to do something a little bit different. But basically, you know, just so you're aware, right about now is when that spidey sense would be tingling. And so if this were code that we were going to keep, it would be pulled out. So we're going to go ahead and get the device context of the window, which again is something we need to draw, and we are going to go ahead and release that. There's a kind of a get and release thing that has to happen here. And by the way, for people who are into resource acquisition is initialization, which remember I said I don't like very much, there are a couple of places where I would be okay with it. I wouldn't fault you for it. If you want to do something like this and have a little thing that's like a DC getter releaser pair to make sure you don't forget the release, if it's something that helps you out and you want to use RAI for that, you could pull this off into a class with a constructor and a destructor. I would not get mad at you for that or disparage you at all. It's totally fine. It's something that you kind of have to do sometimes. So like I said, every programming thing has a place where you may use it. It's really the dogma that gets you. Try not to get into the dogma because every programming practice probably has a use somewhere. It's just usually not something you want to do all the time. You need to know when to use things. And a lot of times when people get into something and they start to assign names to things and do those other stuff, they get carried away, and carried away is almost always bad. So for the RAII people out there, throw you a bone. It is true. I would think that would be a perfectly fine thing for you to do. Now, we need to get the window handle. So we have the window handle here. I'm just going to change this to window, honestly, because I don't know why I called it window handle to begin with. We're not going to have anything else that's called window, so we're just going to go ahead and do that. We have a client rect here, so yes, I should call. In fact, I'm just going to replace that everywhere. It really should have been client rect everywhere. So we're going to change window rect to client rect. We're going to go ahead and, change that. So window rect should be client rect. There we go, just to be a little more concise. And then we actually used it correctly there. Get rid of that. We actually have one. It's not a pointer, so we got to change those to dots. The most useless thing you ever do in C and C++, since the compiler should just know. John already fixed this in this language, I believe. And then we need to pass a pointer to that. So cleaned up all our compile errors, and we should be good to go. Now we are actually rendering the gradient and blitting the gradient. I'm hoping to see something on the screen now, but I don't know if we actually will. So let's take a look and see. Is that animating at all, ladies and gentlemen? It does not appear to be. Why are we sad? Why are we sad, Panda? What's going on here? I must have done something wrong. Let's find out. Are we not blitting properly? Are we not doing, what are we not doing? That stretch blit I think is supposed to do it. I don't know if I have to force it to repaint or not. I'll double check that in a second. But I'm pretty sure we are changing. Oh, awesome. It is just you get excited and you make a bunch of mistakes. So these are getting reset to 0 every time. What a surprise. Got to put those outside the loop, Casey, if you want them to keep increasing. I think that should be pretty obvious. There we go. There is our animating. So we are pretty much in shape now to animate whatever we want. Now, what I would normally do at this point, and this is definitely something that is high on the list of priorities for us to do, is to figure out how fast that stretch blitz, that stretch call is. Now, also we should test this too, make sure we can make it huge, and we can. We can also make it tiny. There you go. And now one of the things that I want to note is basically it goes a lot faster when it's tiny than when it's large, and that's because basically the cost of filling those pixels and stuff like that. But the thing that I actually want to test is how fast we can actually update the screen using this sort of old school way of updating that we're going to use so that we can write the render ourselves. But the problem is I can't really do that. This speed is not representative of what it would actually be. First of all, because our gradient code is super crappy right now, so that's going to slow things down a little bit. But also just the stretch blitz call, the stretch di bits call. It is not a fair measure because open broadcasting system or whatever, the OBS thing I'm using to stream right now, because I have it set to desktop capture, which is what I need to use in order to kind of go through here and show you all the stuff that I'm doing, it makes the machine have like a 0 frame rate. Like basically anything I run, it's super slow. So I can't actually figure out, this might be running really fast right now for all I know and just is getting slowed down by OBS. So basically what I have to do sometime very soon, and I just haven't quite had time to do the research to figure out what one to order, is I need to order a video capture card so we can stop OBS from doing that, so we can actually profile the app on this machine and get somewhat reliable results, because we're going to need to do that for a lot of other reasons. So that's high on the list of things to do, but that is why we can't even tell how performant this technique is even going to be. In fact, you can see when I move the mouse, it slows it down, which would never really happen if this was actually happening without OBS, but moving the mouse causes it to do some kind of thing in OBS and so on. So that's a bit of a problem. We are in good shape today, people. We have an animating window on the screen. Ladies and gentlemen, that was less than 3 hours of programming, including explanations, because Monday, don't forget, was just setting up our dev environment. So 3 hours of fully explanatory programming, that's like 20 minutes probably of actual programming to get an animated window on the screen using only our own code on Win32, where we can now write everything we want. I don't know. People say it takes a lot of work to get something running on Windows. I don't think that was a lot of work. It's a lot of knowledge, yes, but once you have the knowledge, that's pretty quickly. We are inside the 5-minute warning, so I'm going to do one more thing just to show you how this would work. Writing 32 bits is faster than writing 8 bits, ladies and gentlemen, although the compiler could probably do this for us. Let's go ahead and change this to a 32-bit write instead of an 8-bit write. So we're going to change our pixel to be a 32-bit pointer, and we are just going to go ahead and write to it once, like that, in a nice little shorthand. We're going to write to it, and then remember, this is the post increment operator, which means it increments pixel after we have already used it. Dereference, which gives us the pixel that it actually was. Little cleverness there, it is true. But then I am going to go ahead and I am going to actually build this out of bits. So we had 3 values that we actually wanted to use here. There is our 5-minute warning. We had the x plus x offset. We had the y plus y offset. Oh, and I guess we didn't actually have another channel. Right, we didn't actually have another channel. So we need to basically shift these values up and OR them together to produce a single value that we can write out. So what that's going to be is, remember, the furthest up, the highest order is our pad. Then we have 24 bits up. Basically, those 8 bits from 16 bits up from bit 16 to bit 24. That is our red channel, and we were leaving the red blank, if I remember correctly, so we don't have to worry about that. The green channel is bits 8 through 16, so we're going to take that green channel, which I believe was the Y, and I believe X was the blue, right? We're going to take that green channel, and we are going to shift that up by 8. Then we are going to OR it with the blue channel, which doesn't need to be shifted up at all. It just sits where it was. And then we are going to call that our 32-bit value. Oops, I don't know why that cast is still there. Get that out of there. Did not want that. There we go. We are going to call that done and see if we wrote out a 32-bit value properly. Y offset is not capitalized. There. Oop. Well, didn't mean to kill my buffer. Well, you know, sometimes you accidentally hit Alt-K and that kills the buffer. So let's see if that reproduces it properly. There it is. So we've just changed to using a 32-bit write, and if you didn't catch what I did there, we still got 4 minutes left, so I'm going to go ahead and explain that in a little more detail. Basically what we wanted to do is we had a thing that we wanted to write. We wanted to write out for our pixel, which is 32 bits, right? In memory, here is the memory, here is the register. Okay. In memory, right, we have blue comes first, then green, then red, then pad. So when I wrote that out, when I did pixel, I wrote the blue pixel first. I wrote 8 bits of blue. I wrote 8 bits of G. I wrote 0 to 8 bits of 0 to the R and 8 bits of 0 to that, right? So you saw me write blue, green, red, and the old one. But now in the register, these things come in, and they get loaded, and they get loaded flipped around, right, because of the little Indian again. So they're loaded like that. So basically what that means is if I want to find where I'm going to put my blue, it just goes right in the bottom. It's the bottom 8 bits. And then I'm ORing that together. Again, ORing just composites 2 things together. If either of them are set, then it sets it. So I'm going to OR those bits of blue with the bits of green, but I need to move them up to where they would be, and they are 8 bits up, right? They are after the blue. So I shifted them up by 8, and then I ORed them together and outputted my pixel. So there we go. That is that. And we are good to go. That is the end of what I wanted to accomplish tonight. I didn't even know if we'd get to animation, ladies and gentlemen, but we did. And pretty much after we get input in here, that means you can move a character around the screen if you really want to. We'll be seeing how to do all of that next week. Tomorrow, what I want to do on the stream actually is I want to go through and really look at all of this code. I'm going to pull some things out, clean it up a little bit, and discuss what each individual thing does, show it to you in the debugger, go into some more detail just to kind of solidify things. So probably that's what we'll do most of the time on Fridays, is go through and do that solidifying work, talk about things that were confusing people, talk about other stuff like that. But that is a great stopping point for now. So we've got 2 minutes until the Q&A starts. I think I will drink the last of my almond milk, and then we will go to the questions. So good, isn't it? You know, I like almonds too, but I don't really like them that much. So it's interesting that I love almond milk so much. It's kind of confusing. All right. Let's go ahead and take questions, because I think that's all I wanted to accomplish for today. Certainly not going to start something new. And I can't think of anything that we really wanted to fix. Let me go ahead, and I guess one thing I can do is verify that we did not leak any handles with Windows or do anything untoward in that sense. Let me see here. I will go ahead and bring up the task manager, or try to anyway. There it is. Mr. Task Manager, please tell me if my handmade hero has caused problems. Where is Win32 Handmade? There it is. So there is Win32 Handmade, ladies and gentlemen. It is using about 10 megabytes of memory, which is pretty much all the stuff that Windows allocated, I guess, since we didn't do any of that. And and that is staying nice and stable. It's just freeing and reallocating that virtual alloc, which is totally fine. So that is good. No problems there. And we will have more sophisticated ways of keeping ourselves from doing anything untoward. Oh man, look at OBS. What is going on? Oh man. Whoa. OBS is not cool. I really got to get that capture card, ladies and gentlemen. I got to order that because this is not good. Oh my gosh. What is happening? Everything is going haywire on my machine. I don't know if you can see this right now. I don't know what you're actually seeing on the screen, but it is a bit of a disaster, ladies and gentlemen. All of my windows have gone away. Oh my lord. Oh, OBS. Poor OBS, trying to capture all the windows. It is the pop-up, I believe, that is ruining things. Oh, maybe we will have to end the stream and restart it. I don't know if it's going to be able to come back from this. Yes, the Q&A begins now. Thank you for showing us that. Unfortunately, you have destroyed the entire desktop in the process. Poor OBS. I feel for you, I really do. I know Windows wasn't set up for this. Come on, can we just kill our app maybe? Kill our app, please. Get things back to normal. Do something. Somebody save us. Yeah. This is not really OBS's fault, ladies and gentlemen. This is just what happens, I think, when you are trying to stream a bunch of stuff on Windows 7, which I don't think has a good way for OBS to really capture the desktop. Come on, stop our app. Stop our app. Stop the app. Please. Please. There we go. Did that work? No, it didn't work. Ugh. Well, I'll just go to the questions, and hopefully we can answer some questions that don't actually require this, because apparently we are not going to get our desktop back anytime soon. Let's take a look at the actual questions and see if we can get anywhere while this thing is trying to figure out how to get out of its own way. Oh, there it is. We're back. Hey. Well, all right. Well, that just pushed the capture card up to a very, very high priority for me, ladies and gentlemen. One of the things you should do if you are an expert on streaming, and I mean a real expert, and you know some things, please send me an email using the Handmade Hero email address. If you could go to handmadehero.com whenever you would like to do so, go to handmadehero.com and email in a question. And instead of a question, tell me what capture card I should get, because that is the only thing holding me up right now. Thanks to the generosity of people who have pre-ordered the stream, there is money in the account for Handmade Hero that I can use to buy a card, and I will do so. All right. Let's go. Q&A session. Is there a reason you prefer using 0 instead of null? Yes. I find that I like less defines. The less defines, the better. So since 0 always is what null is on every platform that I ever program on in modern times, I just go ahead and use 0. There used to be times when that was not true, I think, potentially, or other things like this, or I don't know. In fact, if Sean Barrett is still on, I don't know. I think he is right now writing a procedural opera generator, but he is the kind of person who likes null and knows those sorts of things. So he may have a good reason why you might occasionally want to use null, but I do not. I would love to learn how to script, but I just don't get it. Can maybe you help? No, I don't know anything about scripting. I don't really write any scripts. It clips to the rectangle anyway. Sorry, I don't know what that means. Standard int. Yes, standard int S. Sylvan. That is what we used. It just took me a while to find it. Let's see, maybe I'm reading too far back here. How come you don't like pound define but type def all of the stint? Oh, I like pound define. I'm sorry, I didn't mean to give you the impression that I don't like pound define. What I meant is I just like to not define things if they already exist. But the reason that I do the standard types thing, oh, my Alt Tab doesn't even work anymore. That's pretty awesome. All right, let me see if I can. There we go. Okay. Wow. All right. Ladies and gentlemen, I really need that capture card. This can't happen again. All right. The reason that I did this is basically that in the old days, these types didn't exist. This is brand new. So I got in the habit of always using my own types because previously you actually needed to define them all because you might be on platforms where you needed to switch this. So you might do something like, if on 16-bit architecture, and then there was, in fact, this sort of thing would happen a lot, right? You'd see something like this. Make sense? You have to do stuff like this. So you always wanted to use this because you actually had to change which types you're using. So these are not superfluous. These are actually there because you had to use them, and that's why I still do it. Like I said, if you were starting your coding practices now, I might just say stick with the _t types because they are what you want, and there's no sense in redefining them. But the other thing that's true is I would argue that this isn't really all that much of a savings anyway because you still have to include standard H. I wish they were just built into the language, which maybe they are in some part of the spec now. I don't know. C. Muratori, what would happen if you call malloc instead of virtual alloc? You would basically go through a crap ton of C runtime library code, and then you would call heap alloc, which eventually would call virtual alloc. So basically, you are just going through a lot of unnecessary code to get the memory. Everyone has to basically allocate memory as pages down at the lower level. So really, we're just going to allocate a bunch of pages with virtual alloc, and we're going to do all of our memory management out of that instead of calling the C runtime library to avoid bothering using whatever it is that they're doing, which is just unnecessary stuff, basically. What's the difference between malloc new and heap alloc? Not much. I believe heap alloc is basically the systems allocator that allocates from the heap, and malloc and new are the C runtime library's way of allocating from that same heap. And so I believe all that malloc and new do is they basically introduce another level of indirection, which I think is usually designed to optimize small allocations and like large numbers of allocations, whereas heap alloc, since it's a system call, can't do a really fast return to you potentially. I don't really know. I don't use those calls, so I'm not really in a position to speak about what they actually do. But if you want to know, you can probably step into malloc and just look at the code like we were doing the other day, where you just call malloc and hit F11 when you get to that line, and you can watch what it does. I went really fast today. Do you think you could go as slow as you did previous days in the future? Probably not. We'll probably have to go relatively fast. But what we'll do on Fridays is we'll kind of do our slow day on Friday where we go through all the code that we wrote over the week and kind of dive into it in more detail. So what I would say is come back tomorrow and take a look there and see if that clears it up for you. But no, we can't go too slowly because otherwise we would really never get anything done. So we kind of have to go and say, well, all right, you can go back, you can watch the stream again, look at individual things, you can ask questions, and then drill down in it, but you're going to kind of have to meet me halfway there if we ever want to actually make any progress. I have to go fast, say everything that's happening as I go, but you may not understand it all, and then you'll have to kind of go back through the stream, think about it, go back and correlate with like the Intro to C course or things we've said earlier. When you don't understand something, you'll have to ask me questions or ask the community questions. We're looking right now at trying to set up a forum for that, but that'll kind of be the way that it has to happen because otherwise we're never going to get a game done. Are we going to use Valgrind later on? Possibly, but we may just use our own homegrown stuff since we may not need something as heavyweight as Valgrind. Let's see. Is the product going to take 2 years? Are you planning on streaming for 2 years? Yeah, we probably will be streaming for like 2 years. What about null pointer? I've never used null pointer, so I don't have anything to say about that. Let's see. Sorry, I'm still a little sick. I'm sorry about the coughing. Really need a cough drop, but they're in the other room. Can you explain why we are using the user32lib and the GDI32lib in the build.bat? I already explained that. Please go look at the other stream. Basically what happened was we need those because those are the import libraries that tell Windows where to get things like stretch_di bits, which is in GDI32.lib. So that is basically the way that we import our function calls to Windows. I talked about that in the little stream. We'll talk about that later when we get rid of Windows.h. Would there be a significant performance increase if you allocated the memory for the bitmap on the stack instead of the heap? Well, performance increase. So first of all, there's no performance increase just because you allocate memory in one place rather than another. The only reason there would be a performance increase is if that memory was already hot for some reason, like it was already in the cache. But memory is memory, so it only matters whether that memory was touched recently, whether or not it's for some reason going to be more efficient. So I don't think the question really makes a whole lot of sense in that way. But the more important thing is we can't allocate it on the stack because anything that we allocate on the stack will go away after we return from that function, right? So when we come in to like Win32 resize div section, the stack is at a certain watermark, right? All of the local variables like bitmap memory size, right, get pushed onto that stack, and our parameters width and height are on the stack. But then as soon as we exit, the stack goes back above it, and that stuff is used for other things. So if we were to allocate this on the stack, as soon as we would return, it would go away. And then we don't have a bitmap anymore, right? It's in memory that will get reused as we kind of move through there. So you cannot allocate stuff on the stack that needs to be permanent. The whole point of allocation is to allocate things that work across multiple functions like that, across different stacks, across different levels of the stack. Did I restart the stream for Q&A? No, we are no longer doing that. We're just doing one from now on. Let's see. I am scanning for questions. Do you know what the page write copy memprotect flag does? Yes, I do. Well, that is one of those fun questions to answer on the Q&A. So basically, I'm going to give you what I believe is the hypothetical reason for it, and you will have to go try to check this, perhaps on the interwebs, or maybe S. Sylvan can tell us, somebody else from Microsoft could maybe tell us. But basically, the reason that you have write copy as a thing, which is basically what write copy is it means we're going to take a piece of memory, and we're going to make that memory be essentially the same as another piece of memory. So we're going to put some data in it, and we're going to have that memory sort of mirror whatever's in there. But what we want to do is when you touch the page, when you actually go to write something to that page, we want to, instead of actually writing to the memory underneath it, we want to silently move it to a new place in memory, a new page, and write to that instead. And I believe that is the flag that you're asking about. Let me double check to make sure I don't give you a completely bogus explanation here. But I'm pretty sure I'm thinking of the right thing when you say that. So let's go ahead and take a look here. I need this to be a little, oops. Didn't mean to grab my Emacs window. Get back over there. I need this to be a little bit wider so it's no scroll bar. Okay, there we go. So I'm going to go over there to look at the memory protection constants, and you said write copy. Enables execute read-only and copy on write access to a map value. An attempt to write to a committed copy on write page results in a private copy of the page being made for the process. Yeah. So basically, the reason that this is in there, and again, this is just me hypothesizing, but I'm just going to tell you why I think it's in there, and someone from Microsoft can confirm this, is basically in Unix, there is a thing called fork. And what fork does is it basically says, I have a running executable. I want to make a second copy of that running executable, right? But I want the second copy to be able to have its completely, to basically, I want them to be able to then diverge. So any of the things that this guy does to the process's memory after the fork, and anything that this guy does happens separately. So it's sort of like just cloning the process entirely. And as far as they are each concerned, they now are completely separate copies. So if this guy changes memory, it's not seen by this guy. And if this guy changes memory, it's not seen by this guy. They're completely separate, but cloned, right? It's just like a cloning machine. In order to do this efficiently, and that was a very important thing on Unix for a while. It's not so important anymore, I don't think. But basically, that was the main way that you got multi-processing in Unix. The way that that's implemented is basically processors started speeding this up by having their virtual memory units go, okay, when I clone a process, I'll just map all the exact same physical memory into the virtual memory spaces of each process, so there really isn't a second copy of the memory. It's basically just one copy. And then the virtual memory unit has a flag that basically says whenever somebody writes to this, right, I'm going to raise an exception. It's basically marking the page as read-only. But what the operating system will do is when that exception gets raised, when the write triggers, it'll go, oh, okay, you actually tried to write to this cloned copy of the memory, which we don't want to have happen because you each need your own copy. Right then, I will basically then clone in the page table, make a new entry for you, and then actually physically copy the bits over to it so that now you actually do have your own copy so that your writes won't be seen by the other process. So I believe that the reason that this is in Windows is because when they went to implement POSIX compliance, and they probably had to implement fork, which meant they probably had to implement this. That's my guess. You should verify it. The download link from Sendile keeps bundling all the zip files together. That is what it's supposed to do. You're supposed to basically get all the days together so that you can pick which one you want. You wanted to say something about size in bytes. Reminder. Oh. You know what? I probably did. Size in bytes. Reminder. Oh, but you know what? My mind, since I had focused so much on the explanations, my mind is just a blank as to what I said during the stream. It's really hard to actually program and talk at the same time. To be honest with you, it's pretty difficult. Size in bytes. What was I even talking about when I said that? Does anyone remember? Because I would love to answer that question, but I do not remember. Oh. Deflated. I'm sorry, I do not remember. If someone can jog my memory, that would be great. Let's see. Let's see. I'm having trouble finding questions here that actually pertain to the code that we wrote. A lot of these are questions about other stuff, which I don't want to do on the end of streams usually, because we got to concentrate on the actual code. So if you could limit questions on these streams, well, maybe we'll do some long streams sometimes where we do other ones. Pitch and stride. So I said size in bytes and talked about pitch and stride. Okay, well, let's see if I can jog my memory at all here. Pitch and stride. So basically in here, yeah, I don't know. I'm sorry, I cannot remember what I was going to say. Maybe I'll rewatch the stream later. Basically, what I was talking about here is pretty basic stuff. Basically, you know, we have a block of memory. I'll just go over again and just say the things about it in case one of them was the thing I was going to say. We want to render to a block of memory. We allocated a block of memory, and basically that memory looks kind of like this, right? It looks like in memory, we have a pointer, and that pointer is bitmap memory, and it is pointing to, right, the pixels. And they are basically the blue, green, red, XX, blue, green, red, XX, blue, green, red, XX. That is the memory for a row, right? One row of the image. And so we basically have width of these, right? We have width of these going this way, right? Starting from from exactly where the pointer is all the way to the pointer plus width times the number of bytes per pixel, which is 4, right? So, you know, we're basically going from bitmap memory 0, right, to an offset of width times bytes per pixel all the way at the end, which is the end of it, which is like right at the end. It's a pointer to like the first thing of the next row. So at the end of every row, if we want to move to the next row, we would actually be right there already because of the way that we've packed these in memory. But if the pitch was something else, so that basically let's say there was padding at the end of the row, like unused stuff at the end of the row for some alignment reason, which oftentimes there can be in graphics. Basically what we do is we take this pointer and we add the pitch to it to get the next row, right? So this right here is row 0, right? Row 0. And then row 1 is going to be the next set of these, right? And each time advancing this pointer is like, bitmap memory plus the pitch, right, to get to the next one, right? I don't know if that makes any sense. So we do bitmap memory plus pitch, plus pitch, plus pitch. Pitch moves us to the next row. So that's exactly what we did here, right? We just said, here's the bitmap memory. We're going to start right at the beginning of it. And then each time through, we're going to add pitch to it to move to the next row. Then this basically fills in the row of pixels. So we take a copy of that pointer, a pointer to the beginning of the row. We go through each pixel of the row and we write it. Now, if we wanted to, you can kind of see what this does, right? It does this. If we wanted to, we actually could just, use, because pixel is basically getting advanced by 32 bits every time. It's getting advanced through these things, right? 4 bytes at a time it goes through there. And so if we wanted to, we could actually not bother keeping a separate pointer, because at the end, pixel is actually pointing at the beginning of the row, because the rows are tightly packed together. So after it goes through all the pixels of one row, it's pointing at the first pixel of the next row. So we could just do, basically say, okay, just use the pointer that you were on. That's the next pointer, right? And that should just work, right? So we could just do this entirely with one. Does that make sense? Hopefully that makes some sense. But I chose to write it in a way that was a little more explicit, just so you could kind of think about that concept of pitch a little bit, because it usually comes in relatively often, and I wanted you to be aware of it. Let's see. You mentioned OX, XX, BB, GG, RR because of Little Endian. Why was the blue channel set in this case and not the padding? So the answer is just because of what the Windows devs decided to do. So again, the way this is in memory order, right? Or rather, I should say, the way that it would be in memory order if you just started typing it probably is you'd store the red, this is memory order, you store the red first, then you store the green, then you store the blue, then you store the pad. That's probably how you would do it, right? Because red, green, blue, pad. It's logical. Because we usually think of red first, green second, and blue third. When this gets loaded in, right, on the Little Endian machine, you get the exact opposite. The red comes in first, the green comes in, then the blue comes in, then that comes in, right? That is what would happen. You'd get BGR, like that. So the Windows devs decided that they didn't like that. They decided they wanted, right, to have it look like this. Now you'll notice what they wanted was just to swap the R and the B. They apparently didn't care that the pad was still at the top. That was okay. They just wanted R, G, and B to be in the same order. That's all they were trying to do there, right? So the pad never got swapped in their brain. So when they actually made Windows and decided what the memory order was, they just swapped the R and the G and left the pad where it was. That is why. So Little Endian was the impetus for them to change. It's because they wanted to read it this way instead of this way. But they didn't actually care where the pad was, so they just left the pad where it was. Could the padding byte be used as the alpha channel here? Yes, it absolutely could be. If we were using what is called a layered window, which tells the compositor that we want an alpha channel, we could actually use this as an alpha channel, yes. Since we don't want our game to have the background show through, we did not do that, but that is something you could do, yes. And in that case, it looks like this, right? So the alpha channel goes in those padding bits. Why are we having a wait symbol on the window? The answer is because we have not set our cursor yet. So if you are wondering why that is happening, that is because we have not set a cursor. And so what we actually want to do is we basically want to do the way you would do that, I believe, is this way. And now we don't have a cursor in the window at all, which is what we're going to want for the game, right? And so the reason that I haven't gotten to that yet is because there's a little bit of others. You don't just want to do that. That's not the only thing you want to do, so I'm leaving that to a little bit later. Could we explain the offset to X and Y? Absolutely. So basically, all I wanted to do is get something animated. So we're still writing the exact same pixels, but we're basically just changing. In fact, I should maybe rename these. In fact, let's go ahead and rename these a little bit. What this really is blue offset and green offset. We're just artificially offsetting the colors that we write so it appears to scroll, right? That's all we're doing. We're just adding an increment that's constantly incrementing over time, right? That's all we're doing. So yeah, those aren't really incrementing the x and the y. We're still writing to the actual places in x and y. We're just using those to offset the colors so it appears to slide. Now, right now, we're not passing y offset at all. We're just passing 0 for it all the time, right? Because y offset never gets incremented. But we could, right? And we could maybe do something where actually we could offset it maybe twice as fast. And then, as you can see, now we would get two ways of panning. You're talking about wrapping your globals. I made a note. I did. Internal versus global variable explain. Oh, well, you know what? Maybe I'll do this now. In case this was the thing I was referring to, I'll go ahead and do this now. So, okay. So, the global variables, some people were a little confused by these. So let me just use the last 5 minutes of our Q&A here to talk about this potentially. So, global variables, the reason that I call this a global variable is because for us it really is going to be global, and you're going to see why in a second here. But assuming that I didn't do these pound defines up here, internal, local, persistent, global variable, right? What you would have seen here was you would have seen like static int, foo equals something, static int, blah equals something, and those would have been how we would do ours, or maybe they didn't get initialized, so they'd just be 0 or whatever. This is what I would have been writing. There wouldn't have been global variable, just be static, right? And basically, what static does is static does two things. The first is it says that this name cannot be used outside of this translation unit, which usually means file. In our case, it won't, which is why I say things are going to be different from us, which we'll see later on in the stream. I don't want to get into it now, but for translation unit, so usually it means like the file, but technically, translation unit means like the file and all files included by this file, like the whole thing. So basically, when we have includes and stuff like that, it's all one big translation unit. So it's not just the file, it's the file and all the things included in that file. Static means that the name cannot be used outside of the translation unit, and it means it is going to be initialized to 0. It means both of those things. We could instead have declared a global variable like that. And what that means is that the name can be used outside. In fact, anyone can use it by just saying extern int foo and saying, hey, there's a foo somewhere, in their file somewhere, some other file. So this is in a completely different file. I say extern foo, and then I can just, mess with foo, and it'll work. And it'll go find this foo that we declared in here, this global variable foo, in here, and it'll modify it, right? You can't do that with static. Other files can't reach in and touch your static variables, right? Other translation units. So that's what static does, right? And then the other thing that static does is if you put it in front of a function, which is why I declared internal. If I do static void some function, basically it doesn't change anything about the function. It just applies that naming part again. It says nobody outside this file can use the name some function to call this function. Now, it doesn't actually mean that other people outside this translation unit can't call the function. They can still call the function, they just can't call it by name. So if we wanted to, in some other code, like let's say in render weird gradient, which is in the same translation unit, I could take some function as a pointer, and I could pass it to some function outside this translation unit. I could pass the address to it, like that, and then that could call into it. So it can still be called by anyone, it just can't be referred to by name in other translation units. That's the other thing that static does there. Now what we're going to do, as you'll see later in the stream, is we are only ever going to have 1 or maybe 2 translation units total. So for us, static means completely global variable. So that is why I defined it to be called global variable. Some people got nervous about that who know C and C++. They were like, you kind of explained that wrong. I'm like, well, yeah, I agree. I probably should have explained it the standard way so people know, which now I hopefully have done. But for us, it's actually completely global variable. It's not even restricted to the translation unit because there's only one translation unit. So all of our code will be able to touch this variable. So it really is truly global. Hopefully that cleared some things up. Static does not give you 0 initialization. You get that by virtue of it being a global. Is that actually true? I don't know if that is actually true. Are we sure about that? If you're sure about that, then that's cool. I would like to get confirmation about that, because I don't actually know. Are extern variables initialized to 0? Let's find out. Stack Overflow is a little bit untrustworthy. I was kind of hoping that I could maybe get something a little bit better than that, hoping maybe someone who referenced the spec. Well, let's see if anyone references the spec. Let's see. This is useless, as always. Oh, maybe that guy referenced the spec? Did he? Well, in C++ here it says that, well, I don't know. Basically, I would like someone, I don't really care about that. I never define anything extern for the most part. So I'm not sure. I'm not going to trust Stack Overflow on that. I would like someone to check the spec. But if you absolutely are, I would like someone to actually check the spec and be absolutely sure that is true before we say that on the stream, because for some reason I remember that not always being true. So I don't know. Do I consider overflowing numbers a good coding practice? If you meant to do it, I guess is what I would say. Basically, like, anything is a good coding practice if you understand what you're doing and you believe that it is a proper usage of the CPU. And since the CPU can do wrapping arithmetic very easily, especially on an 8-bit integer like that, it's no problem. I mean, it can do it on a 32-bit integer just as well. So you should absolutely use that if there's a reason to do so. We are just about out of time, so last question here. Let's see. Yeah, Mechanics says it goes in data as dB, so it's very likely to be 0, but only because Windows zeros was page 4. Yeah, I believe that the person who said that it gets initialized to 0 is wrong, actually. I believe that only statics are guaranteed to be initialized to 0, so I'm really nervous about that. But if someone checks the spec and says that it absolutely is 0, then maybe you can rely on that. I don't know. Okay, someone says they have. Is this actually? I don't know if this is actually someone's sending a link here. Maybe this is a link to the spec. I don't actually know. Let's find out. Copy link address. Let's see here, because I would like to know the answer. I don't ever use it, but let's see. Let's see. Static. If an object that has automatic storage duration, its value is indeterminate, yes. If an object has static storage duration, it is not initialized explicitly, then it gets cleared to 0, as we thought. Well, let's see what happens with an extern, though. Yeah, so it looks like it's not initialized to 0. I don't know. Someone should go do a careful read of the spec, but I believe Dusty Gazongas, I believe that is not correct. Static is the thing that gets you 0 initialization. It being global does not help you. You actually, I think, do need it to be global. Now, granted, you could just do, like this or something, and that would then cause it to be initialized to 0. But if you just declare it with nothing, it will not be initialized to 0, like a static. All right. I think that is about it. Please save all the questions for tomorrow, when we will be going over this code with a little more of a fine-tooth code, and I'll explain everything in very deep detail, and we will clean up a few things and talk about how we want to do that cleanup, because the code is a little bit messy right now. So I had an excellent time coding with you this evening. I am pretty psyched that we have an animating bitmap now that we can do whatever we want with. And we will have about, I think, one more week of Windows coding. Next week will be a Windows coding week as well, because we've got to get sound working. I don't want to start the game without sound. So we're going to get sound working and just do a little bit of work with input so we can have a gamepad and stuff like that. So I think we'll have one more week of Windows stuff, but then we will be in game territory in time for the month of Christmas, which is exciting for me because I'm pretty psyched to start working on this game. I hope you are too. So thank you so much, everyone, for joining me. It has been a real pleasure. I hope to see you all tomorrow. We're going to do 8 p.m., I think, tomorrow again. And then from then on, we'll move the Friday streams to an early stream so that people in other time zones can follow along. But tomorrow we'll do 8 p.m. again, I believe. Watch the Twitter to find out what the time is. And I'll try to get a live schedule up at some point so people know when the stream is up so they know when to come. Again, thank you so much for joining me. I hope to see you back here tomorrow when we'll go over this code. We'll clean it up. We'll talk about anything. We'll sort of tighten down the learning screws on it so that everyone kind of is comfortable with where we're at, because we went really fast this week. That was the goal. We'll kind of try to do those like basically fast through the first 4 days and then take a day of just like relaxing and talking about the code and making sure we're all comfortable with it before we move on. That's probably how we'll do things. And I hope to see you all here tomorrow with your questions. So thanks everyone for tuning in, and I will catch you tomorrow.